Once we have the backbone and we understand the physics of baryons and the importance of feedback, there's essentially three main ways to look at simulations of the universe in large scales. Simulations number two, semi-analytical models, and hydrodynamical models all rely on number one, and therefore number one is really the backbone to all models. The big difference between simulations two, which are semi-analytical models, is that you use very simple equations to model the physics. And this means these models are computationally very cheap. You can probably run one in a supercomputer, sometimes in a matter of minutes, while hydrodynamical simulations, where you use all the physics and no approximations, although you still need subgrid physics because you can't model all the scales, they are computationally very, very intensive. And even in supercomputers, they may take something like months to run. This means that all simulations are based on n-body simulations, and therefore simulations like these are crucial to then make all the other predictions. These are done in supercomputers just using gravity. Most simulations actually don't even include relativistic effects because they're not so important, and all you need here is really Newton's gravitational law. What you're doing is looking at the interactions of all the particles and following how structure will grow. Once you have your prediction for dark matter, one of the very computationally efficient ways of trying to simulate universes is to use semi-analytical models. In practice, what you're doing is solving differential equations. They can be as simple as something like this, that tells you about the first derivative of mass, how a mass is growing in a galaxy is equal to how much cold molecular gas there is, and then there's a time scale to converting gas into stars. Because you're looking at simple differential equations, they're very easy to solve, and because you already calculated all the dark matter framework, then you can actually follow the simulation in terms of dark matter tree, so you can see essentially all the dark matter halos merging to form larger and larger galaxies, and every time that happens, you're actually following all the physics and solving the differential equations that allow you to predict how much mass there is, how many stars there are, and for example, how the star is enriching itself. For these semi-analytical models to produce anything like the real universe, then you really need to include a lot of subgrid processes. You need to introduce equations that will tell you how the gas will cool, how it will condense, how it will form stars, what kind of stars will form, how those stars will evolve, and how the supermassive black hole will grow, for example, or what kind of energy the different processes will be producing and releasing. A nice thing about the simulations is that in principle, you can make all the parameters be related to physics, and because it's quick enough to run, you can make a universe in something like 5 minutes, compare it to the real universe, and then try to constrain some of the physical parameters by trying to get closer and closer to the real universe. But one of the disadvantages of semi-analytical models is that in principle, you could just be adding more and more and more parameters, and provided you have enough parameters, you always be able to match the real universe, and that doesn't mean necessarily that you're getting the physics correctly. In simple terms, what semi-analytical models really do is to get all the knowledge that we covered, or some of it at least, in Physics 263, and actually put it in some computer code that can be run, and then at the end you can make predictions or comparisons with observations. For example, you actually look at how stars form. For example, within a region, when the mass of a molecular cloud exceeds a gene's mass, stars will form. Once they form, they will follow an IMF. There is actually stellar evolution included with the sort of scaling relations that we've covered. So this will tell you when some stars will go supernova. When they go supernova, you actually inject energy into the system. You can compare it with the escape velocity to know what will happen to the gas. And also, as stars go supernova, they also produce dust, for example, and this dust will be crucial for how the gas will cool, and then this will be crucial to then recalculate the gene's mass condition and to know how stars keep forming. And ultimately, all these simple predictions, even though there are many of them and they're all connected, will allow you to make predictions of how many, many galaxies on this backbone of dark matter will evolve with time. In practice, what you will typically be following is essentially going from cold gas that can actually form stars through a process of star formation. And then these stars, some of them, you know how many will go supernova, leading to ejected gas with a given temperature. And depending on the escape velocity, there might be reincorporation or not. This gas will come as hot gas. And if you want to transform it back to cold gas, you need some processes of cooling. But what AGN typically does is it prevents some of this happening. And in some cases, after a few rounds, the gas just becomes hot. If there's no more cold gas, there's no more stars, there's no more ejected gas, and etc. So you can actually predict and understand the conditions that lead galaxies to stop forming stars. Perhaps one of the big limitations of semi-analytical models is the fact that nothing ends off. All the processes need to be put in by hand. This includes environmental processes that we briefly covered in section 14, such as harassment, strangulation, room pressure stripping, or even processes that we call halo quenching, when the halo of the galaxy is just too hot for the gas ever to cool. All these processes need to be put into the code, essentially as equations or conditions that will be triggered once a galaxy or a structure fulfills it. Perhaps one of the big successes of semi-analytical models is the fact by implementing feedback from AGN and from supernova, they were some of the first to actually reconcile the predictions from n-body only or dark matter only simulations with the real universe. And because they can be run very fast, you can even tune some of the parameters affecting feedback, such as, for example, how much energy is produced in supernova events and how much energy is actually locked into the gas that heats it up and actually can drive it off from a galaxy. On the other hand, you can take your n-body dark matter only simulation, and instead of using simple equations, simple differential equations that you're trying to solve, you actually put in all the physics and you run hydrodynamical simulations. Because these do not have any approximations, they take a long time to run, but the advantage is anything that comes out is very ends-off, and therefore it doesn't feel artificial, or you don't need to put in things that are not there directly. And therefore, for many people, these simulations are much more pleasing because you don't need to add things by hand, and anything that comes out can really teach you about what goes on given the physics that we think exist. In these simulations, for example, you can see how a galaxy, pretty much like the Milky Way, is forming without any intervention. So no extra parameters were added. And the only thing that's happening here is whenever stars go supernova, we use our knowledge of the energy that's released, but all the impact and the physics are done directly without big approximations, apart from those at scales smaller than that the simulation can resolve. And what you can see here is what happens to the star and the starlight on the left, and on the right, you can see what is happening to the gas, with different colors meaning different temperatures that can be traced in these simulations. For years, hydrodynamical simulations suffered from the fact that they were very inefficient, and therefore, at best, we would do a galaxy or a solar system, for example. But the last few years saw a lot of progress, and now large hydrodynamical simulations are possible of essentially full universes simulated at a time, and then we can actually study it at the end. Some of the best or the most successful cases have been the Illustris simulation that you see here, and also the Eagle simulation. One of the great advantages of hydrodynamical simulations is that the processes, for example, environmental processes, come out very naturally in these simulations without you adding any environmental effects. Here you can see videos, zoom-ins from the same simulation of some of the highest density regions and the lowest density regions. And it's really crucial to see that all these things are done at the same time, but galaxies that are evolving in the highest densities and those that are evolving at the lowest densities sort of have a different internal clock. Galaxies at high densities evolve very quickly because there's much gas, so there's much more supernova events, the black holes grow much quicker, and the gas around them gets hot very quickly, leading to them getting quenched at the end. While galaxies in low density regions, they essentially evolve much slower, and therefore, by the end of the simulation, most galaxies in low densities are still forming stars. Galaxies in clusters are actually not, and they've quenched. And it's a big success of some of these simulations that these effects come out naturally as a prediction and not something that you need to input by hand and that it's artificial.